things that's changing is our ability to actually find and characterize planets around other stars. So the things that Lee and which Joe work on. So I'm very, very jealous of both of them, because this is a field which has grown amazingly over the last decade. And we're now at the point where we can actually look at the atmospheres of planets around other stars and be almost able to say what they contain. In particular, one of the things that I really look forward to is next year's launch, fingers crossed, of the James Webb Space Telescope, which will really help this field. How about you, Joe?
So continuing to talk about something that's not in my field at all, one of the things that I don't do that I've found really exciting over the last few years has been the discovery of gravitational waves from various different mergers. So continuing to talk about something that's not in my field at all, one of the things that I don't do that I found really exciting over the last few years medium-sized, I think, black hole merger the discovery of gravitational waves and the statistic that's really astonishing is that continuing to talk about something that's not in my field at all. One of the things that I don't do that I found really exciting over the medium-sized, I think, black hole merger discovery of gravitational waves from various different mergers. Continuing talk about something that's not my field at all. One of the things that I don't do that I found really exciting over the medium-sized, I think, black hole merger discovery of gravitational waves and the statistic that's really astonishing. Gravitational waves is very new work. One of the things that I don't do that I found really exciting over the medium-sized, I think, black hole
opened a whole new window on how we can study the distant universe. And at the moment we're learning a lot more about black holes. And that same discovery that Joe was talking about, this gravitational mass black hole, so not one of the and that's really astonishing. Gravitational waves is very new work. One of the things that I don't do that I think it's opened a whole new window on how we can study the distant universe. And at the moment we're learning a lot more about black holes. And that same discovery that Joe was talking about, this gravitational waves on the low end of the intermediate mass range, though. And that's really astonishing. Gravitational waves is very new work. As a way of explaining how black holes form into supermassive black holes, for example. So for me, that's been a really exciting discovery just this week.
Thanks, Michelle. And how about you, Tim?
Yeah, so I think all of those things are obviously really exciting. So I'll go for something a little bit different, and that's the new facilities that are going to be coming online in the next 10 or 15 years. So the ones that are really exciting me, obviously you already mentioned James Webb. But there's also the new ground-based telescopes, so the 40-meter class telescopes, like the extremely large telescope that's being built in Chile at the moment by the European Southern Observatory. That's going to be revolutionary in many ways. And also the Square Kilometre Array, a giant radio telescope that's going to be split between Australia and South Africa. That's going to be just revolutionary in what we can do at the radio scale.
Yes.
How about you, Lee? Is there anything else?
Well, following on a little bit from what Tim was just saying, in radio wavelengths, when you look at the
Hi everyone,
planets,
it's
it
lovely
allows
to
you
see you.
probe down through the outermost layers that we're all familiar with from looking through a telescope. So for the past sort of 40 or 50 years of planetary exploration, all we've been able to do when we look at Jupiter, Saturn, Uranus and Neptune is just scratch the surface and see the colourful cloud tops. But things like the Very Large Array, things like the ALMA facility out in Chile, and also the Juno mission in orbit around Jupiter, they all carry with them facilities to be able to probe down through those clouds and figure out what's going on at much, much deeper down inside these planets. And that's something we've never been able to do before. We're very lucky to be seeing the inner workings of these worlds for the first time. And it's great that it's on our watch. We can go into the lab every day, or we used to be able to go into the lab every day and see new data coming in from these facilities that blow your mind whenever you see them.
And Chris?
We have the next episode of The Sky at Night, which is a week on Monday, is about a secret discovery that I'm not allowed to talk about. So that, but if I'm not allowed to talk about that, then somebody should say exoplanets, because over the last 15 years or so, it's been amazing to come to the realization that the variety of planets that exist in the galaxy is much greater than I think many people predicted. We see planets that are very close to their parent star, planets that are different sizes from the ones we have, planets in all sorts of environments. And watching the science of planetary physics build up on those discoveries and understand what these discoveries are telling us about our solar system has been just amazingly exciting. It's been a great time to be an astronomer. So I'll just say the most exciting thing is anything to do with exoplanets.
Thank you. Elizabeth?
Well, you've left me the hard job, but I'm actually going to come at this from left field slightly. All of what has been mentioned already is fantastic and groundbreaking and wonderful, but we wouldn't be able to understand any of it without the fantastic work being done by theory and computational astrophysics that provides the framework and structure that lets us interpret.
Oh, I think we've just lost Elizabeth, at least I have.
Yeah, I can't hear her either.
That's a shame. Hopefully we'll catch up with Elizabeth in a second. This is one of the perils of using Zoom. Oh, sorry, Elizabeth, we lost you there at the very end.
Oh, well. Let's just say computers and stop there.
Excellent. As half a theorist, I'm very happy to actually somebody to mention theory in there as well. Okay, great. I'm going to come back to something that Chris said a little bit later, but before then, let's have a look at some of the other questions. So I think this first question is probably best directed to him. This is from Paul Shepherd, who asks, how do supermassive black holes with masses of millions or even billions of mass of the sun in the center of galaxies form?
Yeah, this is a really, really good question. The answer is that nobody really knows. There's a couple of competing theories. You could classify them as two different theories or three, depending on who you speak to. The first theory is that you have a normal star that lives through its life and it explodes in a supernova, and then the remnant collapses down to a black hole. We know this happens in our own galaxy, and those black holes then would be up to, let's say, 100 solar masses in size, maybe a little bit smaller, and then over time those could, in principle, accrete enough material from around themselves, from the clouds of gas that live around them, especially at very high redshift. If enough of that material can be made to fall onto that black hole, you can grow it. It's actually really, really difficult for that black hole to eat enough material in the amount of time that the universe has been going to reach the sort of masses that was talked about there, so millions, billions of solar masses. Because every time something falls in, it gets hot as it falls in, and that radiation it then emits will push back stuff that's falling in behind. So there's a limit to how much black holes can eat. And so that really sets the sort of bounds on this. So to get around this, there's a couple of ways you can do that. Maybe in the very, very high redshift universe, the stars that lived then were different from how they are now. So Elizabeth works on this, and Steve, I think, as well. So those stars, they could be very, very massive indeed. So maybe when they collapse down, you form much bigger seed black holes that can eat enough material in the time available to become that massive. Alternatively, perhaps what you have is lots of these small black holes that end up coalescing.
Are you on YouTube or Zoom?
Over time in a dense environment like the very center of a galaxy. So you can really start to form that from each mergers of many smaller black holes. And then finally, there's a really extreme theory where at very, very high redshifts, you can, in principle, in simulations at least, get conditions that allow the gas to collapse directly to a black hole without ever having been a star. That's called direct collapse. Now, we don't know. Finally, there's a really extreme theory of active research going on.
This is what I've done
Looking
here.
at these sort of very, very high redshifts, you can, in principle, in one way you do this, you get conditions that allow the gas to cluster emerges. That's really exciting what's happening right now.
That's our control panel.
Thanks
Ignore
a lot,
that for a
Tim, that was
moment.
great.
So I'm running
I think
Zoom,
the next question is
and
for
then
Lee.
running OBS, and
This is an
OBS is
anonymous
streaming
person
back to
asking,
YouTube.
what does Juice hope to
And
discover,
that is working,
and how is it different from Juno?
but it's
Okay, so
protesting
the Juno
about
spacecraft,
YouTube
when it
not receiving
launched
enough
back
video
in
to maintain smooth
2011,
streaming.
was really dedicated to the study of the planet
No,
itself.
and I think
It's
that might
looking
be
at
because
the
we're now trying to
interior
stream
structure of Jupiter.
up
It's looking at the
from
magnetic
this
field
side.
of Jupiter,
And I
and
don't
it's
know what
looking
our
at the
uplink speed
atmosphere
is.
of Jupiter, sort of filling the gap
We have
between
also
external
busted the
environment
URL.
and what's going on deep down in its centre.
Well, this
So
one as well,
Juno
because
is
it's
in
my
a
stream.
orbit, very, very
Yes.
close to the planet, and
I'm not sure that-
close, 150 feet, 80 or so. Juice, on the other hand, is not really focused on the planet Jupiter itself. It's more focused on the environmental conditions that we're going to explore on the surfaces of the icy moons. So its intended target ultimately is Ganymede, the largest moon in our solar system and the only moon with its own magnetic field, which means that you get these incredible things like auroral light shows on the surface of an icy satellite, which we don't see anywhere else. Juno, on the other hand, spends so much of its time close to the planet, it doesn't have the opportunity to explore those icy moons. Now, JUICE carries with it an ice-penetrating radar, which I think is one of the most exciting instruments on board this spacecraft, because what that can do is it can probe, hopefully, up to 10 kilometers down through the icy crust of Ganymede, the icy crust of Europa, and potentially the crust of Callisto as well. And what it's looking for are small pockets of liquid water that might be trapped within the ice. And if we're really lucky, it might see the transition between the icy crust and the deep, dark, hidden oceans that lie beneath those icy crusts. And those oceans are maybe some of the most tantalizing places for planetary explorers right now, because they might have all the right ingredients for what we call habitability. Not necessarily life to exist, but habitable conditions away from the Earth. And I think that's something that all planetary scientists and scientists in general are excited about looking at. So that's why JUICE is going to launch in 2022, touch wood. We'll sail onto Jupiter by 2029 and spend 3 years orbiting Jupiter and a final year in orbit around Ganymede. So watch this space.
Fantastic, thanks, Lee. I mean, I've always been excited in the icy moons of Jupiter since reading Arthur C. Clarke's novels and seeing 2001: Space Odyssey and 2010: A Space Odyssey when I was young. So it's really fascinating to see this, and really hope we find something really interesting.
One thing I noticed in that question, Steve, just before we finish, was that our anonymous attendee was wondering whether it was NASA who had chosen that particular mission. Now, I want to set the record straight. That is a European Space Agency mission, and we're very, very proud of the fact that it's Europe that's going to be going to explore the icy moons of Jupiter in the 2020s.
Well done for capturing that, Lee. That is really important. The next question is quite a general question. So this is from Jessica Connor, who asks, if you're interested in astronomy but are maybe not so fantastic at physics or astrophysics or maths, what is one of the ways that you could get interested in astronomy? So obviously this is a very general question, but I think, Michelle, do you have any comments on this first of all? Then maybe see if any of the other panel members want to say something.
So one of the things I like about astronomy is it's somewhat fundamental in that we're all just looking up at the sky, and then it's just how much detail you're looking at the sky in. So I do think it's quite a visual science in many ways. And it's also quite a creative one because, you know, in other sciences, you have these experiments that you can design, set up, measure, run and again and again and again. But in astronomy, the experiment is basically the universe. It's already been run. And then we're just trying to find innovative ways to look at it, to learn about how the universe formed, how everything's been evolving, and stuff like that. So I think for me, that's kind of one of the, focusing less on the, you know, you have to be great at maths, you have to be great at physics. It's also just about like people's interest, I think, in how everything got to look the way it does and what else is out there in the universe. So it is, you know, I think there's a lot of visual aspects, creative aspects, and sort of a lot of imagination as well when you're trying to do something like astronomy. So I think it sort of transcends physics and maths as well, I think, and it's very accessible, I think, to a wide range of people.
Do you mind if I add to that a bit?
Yeah,
I think it's so certainly if it's just an interest in astronomy, then go and look at the sky. That's where lots of us started, and it's still the thing that inspires me to pay attention. I also think we're very lucky in astronomy in that occasionally the details need to be in mathematics, but most of the ideas that we wrestle with are well described in words and in other ways. And there's an amazing variety of people writing really well on cutting edge science in astronomy. So I would just try and read as much as possible. That's not true in other areas of science, and I think astronomy can be translated for anyone. I think I'm not sure if the question was about career in astronomy, and the one thing I'd say is that if what inspires you as a career is getting involved in astronomy, but you don't think of yourself as a physicist, there are many routes to play a part in adventures like Lee's mission to the Galilean moon. Space agencies need all sorts of skills. Big projects need all sorts of skills, from engineers to software people to people who just know how to organize big projects. And so I think if you want a career in space, more generally, not literally in space, that's a bit different, then there are lots of different ways in. And I think thinking creatively beyond just, I'm going to be a physicist with a blackboard and solve equations about black holes, I think that's a good idea.
Can I just pick up on something that Michelle said, and that was the word creativity, because one of the things that's impressed me looking at data coming back from spacecraft is that a lot of the images are available to the general public immediately for them to play with. And what they do is they take these sometimes rather, I hesitate to use the word, but bland images of a planetary surface, and they're able to manipulate that using photographic skills, software skills, coding skills to pull out absolutely exquisite detail that the rest of us might not have been able to notice. So I've been really impressed in that sort of citizen science aspect that's coming from a perspective of creativity and a lot of software design to pull things out of data sets that we might have missed otherwise.
Thanks, Lee. Does anybody else have anything else to add there? Well, if not, I'm going to ask a slightly controversial question, maybe a little bit of a mean one now. So this is more of a question from myself, but it's kind of been picked up by Chris already, and a few people have kind of mentioned aspects of this. So as I understand from Chris, there is a big announcement due on Monday, which has caused
a week on Monday.
A week on Monday. Oh, okay.
Yep.
But it's caused the sky at night to be moved by day in order to presumably avoid the embargo and actually be able to report on this. I'm going to ask all the other panel members, other than Chris, to speculate what you think this discovery might be.
I'm going to hide my video because I have the worst poker face in the world. So I will look forward to finding out what people come up with.
I'm pretty sure I know what it is because I think I know some of the co-authors, so I'm also going to keep quiet.
Ooh, okay. So, well, I now have two guesses, so I'm going to start off with my two guesses. One of these is going to be the discovery of a very large object, maybe even something that would be classified as a planet on the outskirts of the solar system, which will be Planet 9 or Planet X. Actually, I'm just going to stick with that one. That's my guess. How about you, Michelle?
I was going to guess the same thing, actually. I mean, yes, that would be my guess for what is likely. If I would have something that would really excite me is even more, it would be that someone's discovered dark matter, but I feel like they wouldn't be able to keep that a secret. So
yeah, I agree. How about you, Tim?
Yeah, I think those are really good guesses. If I had to go for something else, maybe some interesting signature has been seen in the atmospheres of some of the solar system planets or moons, some gas or something, or the rover on Mars has detected something interesting. That would be really cool.
How about you, Lee?
Well, I see a lot of press releases about us discovering Earth 2.0, and it's never quite as exciting as maybe it's made out to be. Maybe it's not quite Earth-like in that regard, but maybe this time they have actually found the Holy Grail and found a world that's similar to our own Earth, with a similar sort of atmosphere, in a similar sort of orbit, with a similar sort of temperatures. Maybe that's what they're going to talk about next week.
Elizabeth, do you have any ideas?
You keep leaving me for last. It means
I
I'm
can
running.
always deal with alphabetical order.
I was also going to go with biosignatures, possibly from exoworlds even, rather than solar system worlds. It's hard to say, but the sensitivity people are getting on exoworld atmospheres these days is very good. A left field suggestion might be something on the gravitational wave side, but realistically, I don't think there's anything coming up that I wouldn't have heard of, but I might be wrong.
Thank you. I enjoyed all of the speculation. It's
Steve, when Chris turns his video back on, we should ask him whether it's aliens or not.
I am literally forbidden to say anything.
He does have a terrible poker face, you're right.
My worry was that since it was 2020 and given everything else that was happening this year, we were going to see an asteroid coming towards us or something.
But no, I'd be shouting about that. My favourite suggestion is that astronomers have discovered that it's still April. which would explain an awful lot about this year. So,
Okay, great. Thanks everyone again. I think now we've got a good question from Michelle. So this is from Jay Land, who asks, can we see the effect of dark matter or even dark energy on galaxies in the local group?
So dark matter in the local group, yes. So I would say that it's probably fair to say that the main or even only constraints that come on dark matter, well, not only, some of the main constraints that are coming on the presence and the properties of dark matter at the moment are coming from astronomy, and largely from studying how galaxies move and how the stars within galaxies move. And so Andromeda is actually one of the galaxies which Vera Rubin actually studied how fast the stars are moving in its disk. So it's a big spiral galaxy, just like ours, and stars spin around the center. And by measuring how fast they spin, you can work out how much mass or how much the galaxy must weigh. And when looking at galaxies like Andromeda and other spiral galaxies in the universe, Vera Rubin showed that all the disks are spinning so fast that they all look like they're about to just sort of spin themselves apart, because there's not enough mass or stuff in terms of stars and gas to hold all that together if it's moving so quickly. And so that was really one of the observations that sort of convinced the community that there has to be a whole bunch of other stuff that makes up galaxies, like Andromeda, like the Milky Way, that we can't observe directly using light. And so that's where dark matter, the need for dark matter really came from, or was sort of, at least the community began to agree that we needed dark matter. And so within the local group, I actually study a lot of very interesting galaxies that are far smaller than the Andromeda galaxy and the Milky Way. So the Milky Way has 100 billion stars, 100 million stars, sorry. The galaxies I study have more like a few tens of thousands stars. And they're mostly made of dark matter, so they have very low numbers of stars. So you can use the stars to really measure how much dark matter there must be in the very centers of these galaxies. And that helps us much better understand the properties of the dark matter particle, so how massive it must be, how self-interacting it must be, and properties like that. So there's lots of studies of dark matter within the local nearby universe that I would argue are placing some of the best constraints on the properties of dark matter. Dark energy is not something we tend to measure so much in the local group. I think the evidence for dark energy comes from studies of galaxies much further away and from studying supernova explosions in a range of galaxies, I think. And I know much less about dark energy, but I also think that's true of most astronomers.
Okay.
That's great, Michelle. And yeah, just to agree with you there at the very end, dark energy, we really need to kind of be away from the gravitational influence of matter. So when we've got lots of galaxies close together, it's very difficult to discern the effect of dark energy. So we're looking on much larger scales. Okay, so another, I guess, more general question here, which I might target Elizabeth, because she was feeling left out of being always at the end of the alphabet. But obviously I know that more than she does. Next question is, if invited, what would you like to contribute to the next golden record? And I guess this is an allusion to the golden record that was part of the Pioneer 10 and 11.
It was the Voyager ones.
The Voyager ones.
Yeah.
So Elizabeth, do you have any thoughts on that?
Yeah, it's a really good question. And it's one that actually surprisingly comes up surprisingly often in things like science fiction. So Arthur C. Clarke wrote a story, for example, of human beings uncovering an archive left by an alien race that knew they were going to be extinct. So I actually, with groups of students, set them this question: what would you try and preserve of Earth culture? And it's always surprising the answers that come back. You could argue for science, but arguably any scientific culture, any culture capable of finding and decoding our archive would have better science than us anyway. So you're really looking at arts and literature and things which cause emotive reactions, not necessarily just cultural ones. I'm not sure I could pin it down to one article, but I do think it's a very useful question for making us think about what we value of humanity.
Yeah, it's a fantastic question. That's a fantastic answer, Elizabeth. Yeah, really, thanks for that. This next one, again, it's not your area, Joe, but I'm going to direct it at you because I know obviously you've been an RAS counselor in the past, and this is something which is the RS is thinking about right now. But what are your thoughts on the large satellite constellations, including Starlink and OneWeb, which I now believe is partly owned by the UK government, so maybe there's conflicts here. What do you think about those? And maybe some other people can comment on these as well. Fortunately, I'm a space-based astronomer mostly, so I don't worry as much. But how about you answer first?
So there is a lot of concern, obviously, because it's becoming apparent that there is significant contamination from these satellites in images that are taken from the ground, and it's not necessarily trivial to subtract those effects from the image afterwards without losing some of the information that we're looking for. I think there's actually another separate concern as well, which is mainly a consequence of the fact that this is completely unregulated. And that is that the more stuff we put up there, the more likely there is to be a collision. If you get collisions in orbit and things break up, then you get lots and lots of debris in orbit, which is problematic then when you want to launch something else because it can cause problems with the launch. And obviously, if you end up with a lot of very diffuse debris, that's going to be far worse for our view of the sky long term than having a discrete number of things that you know are going to cross at a certain time. So just populating orbit with that many satellites is problematic in itself, actually, for lots of things. Chris will know. We had a Dot Astro conference just over a week ago, and I was actually part of a hack group that wrote a very snarky song about Starlink, which may make it onto the wider internet at some point when we've sort of polished it up a bit. So watch this space.
Thanks for that, Joe. Does anybody else have any thoughts on Starlink?
Yeah, sorry, Liz, after you.
Oh, I was just going to mention I'm involved to some extent with gravitational wave transient follow-up. For that, you have to map very large areas of sky, and you have to do it quickly. And any wide field imaging project like that at the moment is subject to really quite extensive contamination from these Starlink trails, particularly when you're looking for things that are varying in brightness between images. If you have satellites going across the image, yes, it may only affect a small amount of the image, but if that's going across what you're looking at, that can be catastrophic for time series and time analysis.
Yeah, so I'm involved in the Vera Rubin Observatory, which is this big survey that used to be known as LSST. That's going to survey the whole sky that's available to it every 3 nights. And the estimate is sort of in the at least the hundreds of thousands of dollars to deal with this problem just from Starlink. I'm worried slightly that astronomers as a whole have got ourselves at the wrong end of this, in the sense that at the minute these companies are planning to launch satellites and working out how to mitigate those effects. So SpaceX have actually been reasonably cooperative in thinking of ways to make their satellites fainter or to try and reduce the impact on astronomy. And there was a big report out about a week ago that explained all the ways that such companies could be nicer to astronomers. In particular, sort of making them fainter makes it easier, and it means it doesn't disrupt the aesthetic enjoyment of the night sky. But actually, the thing that bothers me is that none of that consideration happens before launch. If I want to put a new motorway across a hillside, I have to explain to the people living there why I want to do that and what the benefits and costs are going to be. I think we need desperately to get to the point where internationally, if you want to launch satellites, you explain, as Joe says, there's a cost to other satellites, there's a cost to people on the ground. And then you could say, okay, if I'm going to provide internet for everyone, and here's my business case, and it makes sense, then maybe that's okay and that's worth doing. But at the minute, we have satellites going up and then we're relying on goodwill, and that's going to break down in something that's run in a commercial way. At some point, these companies are going to decide that it's cheaper not to bother that much more about astronomy. And then the world, where we want to do things like keep an eye out for asteroids, is going to have to take consequences. And we need to get a planning regime for space into place quickly.
I think that's a really good point, Chris. Yeah, and something that hopefully the learned societies and government and companies can take forward into the future. I just wanted to share two thoughts that I have on this as well, and they're very different from from everybody else. So actually, I recently saw one of the Starlink constellations. So shortly after launch, when they launch, they actually launch a group of satellites. And so shortly after launch, you actually see several satellites kind of crossing the sky relatively quickly. And it was absolutely amazing just watching it. Just watching these things that humanity put in the sky. You don't just see one moving across the sky. You can sometimes see a whole train of them moving across the sky. And I mean, my 9-year-old loved that. I think more than just looking at the stars themselves, actually seeing the presence of humans in space, I think was really amazing. So although it does have a whole load of detrimental effects, these things can still be very beautiful. And my second and kind of more spurious point was the name Starlink is something that the UK astronomy community have had for a long time. So Starlink was the name of our kind of software service dating back to the 1980s. Did they actually pay us for the patent to this? Obviously, this is a bit of a joke, but they did not invent that name. Okay, but moving on to the next question. This is another good question for Lee. And this is, again, an anonymous question, but it asks, could a tidally locked exoplanet have liquid water on its surface in the region between the heat and cold? I guess the kind of sun-facing side and the anti-solar side.
One of the things I've learnt when talking to the extrasolar planet community is that your expectations for these things often get wiped out very quickly when confronted with the pantheon of different types of planets that we have out there. So, frankly, I would say yes. Why not? You can imagine circumstances with the thousands of planets we've currently detected and the millions of planets that we currently haven't yet detected, where that kind of circumstance might exist. Searching for the signatures of water vapor in a planetary atmosphere is about as far as we can get right now. But Joe might be able to correct me if I'm wrong, but I've heard of efforts of trying to detect the glint of standing bodies of surface liquids, potentially water, on the surface of another world, just like we did for the glint of sunlight off of Titan's methane seas, for example, with the Cassini spacecraft. But I would say that your imagination can run wild when it comes to extrasolar planets at the moment. I don't know if Joe has anything that you wanted to add there.
Yeah, you're right that kind of observation is planned, Lee. I don't think it's very close to fruition because we don't have the technology to do that at the moment, but it's certainly planned. And yes, I agree that it's entirely possible to have liquid water on a tidally locked planet as well. I think one of the key things is that in our solar system, we've only got one tidally locked planet, and that's actually, I'm not even sure. Is Mercury tidally locked? Can't remember.
No, it's a
It's in a weird resonance, right?
Yeah.
So it's got some
okay,
aspects.
I knew
Yeah.
something. But anyway,
with the Earth,
the moon is tidally locked, but Mercury, being the closest to the sun, does have one very hot side and one very cold side, which is the kind of scenario that I suppose you're picturing here for this tidally locked exoplanet. But the reason Mercury has such a big temperature difference between the day and the night is that it doesn't really have much of an atmosphere. Atmospheres are really important for transporting heat from the day side of a planet to its night side. So if you had a tidally locked temperate planet with a substantial atmosphere, then the temperature might not be so drastic on the day compared to the night. So you might be able to have actually relatively stable conditions, depending on how thick the atmosphere is and how efficient it is at transporting heat.
that's great. Thank you all. So again, we have there's actually been quite a few questions asking about how the panel got into astronomy, some more specific questions about maybe what degrees you studied and what your career path was. But I think just to start off with, and I'll ask this to the entire panel, we have a question from Jessica Connor who asks very simply, what inspired you to get involved in astronomy? And I'm going to get the panel to answer this in reverse alphabetical order. So I'm going to start first, followed by Elizabeth. So my interest in astronomy actually began when I was probably about 9, and it was actually from playing a computer game. And it was playing a computer game called Frontier, which was the sequel to the very famous game Elite, which was kind of the very first space simulation. And I loved playing this game because you could fly to different stars and different planetary systems. Now, this has been done in loads of games, but what Frontier and Elite and that whole group did very well was actually making it as accurate as possible. The planetary systems that they imagined and the galaxies that they imagined was kind of real. So you could fly to these different stars that were all different, and we know that stars are all different according to their masses. So that was one of the things that really got me interested first of all. And then after that, I guess the honest answer is, when I was a university student studying physics, I had some very, very good astronomy lecturers who kind of encouraged me to take it up. But how about you, Elizabeth?
Science fiction. I basically was surrounded by science fiction as a child, exposed to all of these ideas and concepts, and programs like The Sky at Night were on television as well, and I saw those. My parents watched them. I think I grew up accepting space as a normal part of the world around me and wanting to know more about it. I took a brief detour into archaeology, but then rapidly turned back towards physics because I realised that while the human past is interesting, the deep past is even more so. And that's how I ended up in astronomy.
A couple of things. One was I was a kid who looked at the stars. So I remember standing out when I was 6, 7 and 8 looking up at the night sky. But really the thing that turned me into an astronomer was the sudden realisation during a talk by Patrick Moore that astronomers didn't know everything. Somebody asked a question. He said, well, I've told you what we know, and if I came back in 10 years' time, it would all be completely different, because the truth is no one knows about these subjects. And I was about 11, and just the idea that science was something that was ongoing, that there were still discoveries to be made, just clicked for me. And luckily, I remain in complete ignorance about most of astronomy now, and I still enjoy it.
So I was never lucky enough to own a telescope. In fact, I was in my mid-20s, I think, before I even had an opportunity to look through a telescope for the first time and saw Saturn. But a little bit like Elizabeth, science fiction was an enormous part of my life when I was a child and when I was a teenager. Things like Star Trek and Doctor Who and Star Wars would transport me to other worlds, and I could perfectly well imagine that was in our future as a civilization, and that I might be lucky enough to live long enough to see it. And it was only then during my sort of university career that I realised that there was a possibility of me having a career continuing to study potentially towards this end.
Tim?
So for me, I think in a way it's slightly different than the things that everybody else has said, because I didn't want to be an astronomer when I was growing up. I studied physics, went to study physics at university because I wanted to be a pilot. And I didn't want to go through the Air Force because that wasn't really for me. So I thought, okay, I'll get a physics degree and then try and be an airline pilot. But what I discovered when I was doing my physics degree, I did a physics degree, I didn't do an astronomy degree, but luckily there was some astronomy modules in there. And I just had really good teachers. And it just dawned on me that astrophysics is this real sweet spot, for me at least, where you have to use all types of physics. You have to use your understanding of gravity, your understanding of mechanics, your understanding of quantum mechanics, all of the parts of physics that you think of as some people might see as being disparate. You have to use all of it in physics because you're studying the whole in astrophysics, because you're studying the whole universe. And that really spoke to me and got me really excited and interested, and then I just took it from there, really.
Thanks, Michelle.
Yeah, I guess my story is a bit more like Tim's as well. So when I was younger, I wasn't really into science at all. In fact, it was a couple of years ago, me and my mum found one of my primary school reports where the teacher said, Michelle has no interest in science and would much rather be writing stories. And I think that remained true for quite a while. And then in senior school, I was still trying to decide what to do for my, what I wanted to do with life. And I decided that I wanted to take maths, physics, chemistry and biology as my A-levels and either become maybe some kind of scientist or a doctor. And I was quite into watching ER at that time, which was an American hospital show. So I thought maybe I could be like a surgeon or something. And I had to move schools to do those A-levels together because I went to a particularly bad school with very few science teachers initially. And then when I moved to my new school, I had to sign up for physics, and the head of physics told me that I should really think carefully about that because typically only boys do physics. And I think if I'm being completely honest, I don't like being told what I can't do. So it made me really determined not only was I going to take physics, but I was going to be the best at it. And that was certainly true for my A levels. I was much better than the boys in my class. But then because I sort of really threw myself into it, I got really more into physics and into astrophysics in particular. So then I decided that's what I wanted to do for my degree. And then I just really enjoyed it. So I just kept doing it for as long as I could. And that turned out to be, at least up until now. So as long as this panel goes okay, hopefully I'll still be doing this tomorrow as well.
Thanks, Michelle. That's a great answer. Joe?
I was a lot like Michelle when I was little. I definitely preferred writing stories. I thought I was going to become an actress when I was a kid, which, you know, actually has served me quite well in terms of giving talks and things. Public speaking's always been a part of what I do that I actually really enjoy. My dad is an astronomer as well, so I was always interested in astronomy, but not particularly keen on physics or science more generally when I was younger. I had a fantastic physics teacher when I started my GCSEs who, I don't know why, but recognised that that I had some real potential to be very good at physics and would not shut up until I agreed to take it for A level. And during my A levels, I got a Nuffield bursary, which I think still exists. So I got a bursary to go and do a research project over the summer in the middle of my A levels. And I was fortunate enough to get to work with some of the team at the University of Leicester who developed one of the instruments for the Beagle 2 spacecraft that launched to Mars in 2003. So I spent my summer working on hypothetical scenarios actually for what that instrument might be able to detect. And I had the best time. I had a brilliant 6 weeks doing that. And I came out of that and I said, I want to do planets. I want to be a planetary scientist. That's it.
That's great. Fantastic. So can I do alphabet back? Yes, you are the last person in the panel. Sorry, I can't really do the alphabet. I'm not very good. I can do numbers, not words. Great. We've got another question here. This one I think is best answered by Tim. This is from either Anthea or Rachel. How do galaxies sometimes collide and merge, and how much destruction results from such a merger?
Yeah, so we do see around us when we look out with our telescopes that galaxies do sometimes in their course through space, they happen close enough to one another that their gravity results in them being captured. So they start to influence each other, they become bound to each other, and then they will spiral inwards and merge. That could take a long time, or it could be very quick if they're aimed at each other to begin with. As for how much destruction happens, that's actually a really interesting question. So galaxies, although if you look at the example that here, this is a nice galaxy, it looks like a solid object, but actually it's not. It's full of empty space. So all of the stars in the galaxy, you could collide a galaxy together, and the likelihood is that none of the stars will get anywhere close to actually colliding with one another. But that is not true with the gas that's in galaxies. So galaxies are permeated with clouds of gas and dust that are rotating around the center of the galaxy in the same way as the stars are, similar way to the stars are. And those clouds are volume filling, like the gas that fills your room right now that you're breathing, it fills the whole space. And so those clouds can collide. And when they do that, there's a lot of fireworks, you can form a lot of new stars, and that gas all falls to the center, so it becomes very dense. And you actually get these things called star bursts, where you form lots and lots of stars very, very quickly. And those are often triggered, at least in the local universe, by these types of mergers. So although individually there's no destruction from the hitting, when we collide with the Andromeda galaxy in a few billion years' time, you shouldn't worry about the Earth hitting anything, because it won't. There's too much empty space in galaxies. The clouds of gas do, and that does have effects on the galaxy.
Thanks a lot, Tim. Yeah, I guess so. When galaxies actually collide, it's not so much destructive. They actually create new stars, or it triggers the creation of new stars. So these big, what we might think of as being destructive as before, are actually these creation events. And we know that a significant fraction of the stars in the universe are actually created in these events. Okay, so we have another technical question here. I think this one is, best answered by Joe. And it's from Anonymous, and it asks, could you explain how a coronagraph looking for exoplanets works?
Yes, briefly. So the way a coronagraph works is it actually, you think of a normal telescope, what you want is to let all of the light through, right? So you don't want anything in the way. A coronagraph deliberately puts a physical stop in the middle where the center of your image would form. So if you look at the star and the planet and you point the star in the center of what you're focusing on, it actually prevents the light from the star from hitting your detector. It's not just as simple as blocking the star, because if you've got a sharp edge and light goes past it tends to diffract. So you get lots of sort of fuzzy interference type patterns around it, which you also have to remove. So it's not just a single stop. It's usually a single stop and then at a different place in the optics there's a ring that removes some of that diffraction. So basically what you're doing is you're blocking the light from the star, and the planet is off center in the image. So the light that comes from the planet still makes it onto your detector. And the reason we have to do that is that stars
planning on doing it again. So we're going to have a whole series of smaller conferences over the year and then a big one again next year. Again, because even without the pandemic, there are good reasons to do this. So minimizing international travel, which is particularly difficult, obviously, in terms of the environment, people with caring responsibilities. So I think in many ways, the pandemic will make us better. It will make us, force us to do things in a different way, which actually increases equity. I'd just like to add my final comment on all of this is that I remain to be I'm counting down the minutes until Monday when my children return to school and I can actually do some work. What time I've had for work over the last 6 months has really been focused on teaching. So having to move my teaching online and look after my students. And as much as I love my children, I'm craving to get back and actually do some science. And so that will happen on Monday. And again, thank you for all the answers. I think I'm going to ask this question to Elizabeth, but what does an astrophysicist actually do on a daily basis?
Sit in front of a computer. Fundamentally, most of us spend most of our time sitting in front of a computer. These days, many of us are dependent on data from big telescopes and big missions, and that data is collected remotely and communicated to us electronically. So even if we're looking at observational data, we're doing it on a computer at our desk. Having said that, there are still a number of small to medium-sized telescopes still in operation. Warwick runs a 1 meter telescope and the gravitational wave transient follow-up I mentioned, and indeed an exoplanet search telescope. So a number of my colleagues in my department are involved in hands-on data collection, but even they, I would say, spend the majority of their time looking at a computer. But what makes it worthwhile are those moments of realization or discovery, or really being the first person to see something or to think about something, that adds a sense of wonder to what might otherwise be more mundane office work.
Thanks for that, Elizabeth. So, sorry, I've just lost my next question. Okay, so I'm actually I'm going to direct this one at Chris, and I'm going to try and merge a few questions together. So when do you think we will go back to the moon? What might the benefits be? And do you think we should go to Mars?
So, assuming this is crewed rather than robotic exploration. So, let's start with the moon. NASA say that they're going to get there by 2024. That's not going to happen. There's just not the money in the program to do that. And there's an election in the US, which will change things, I hope. So that's not going to happen. I would expect, though, the Chinese are pretty serious. And I would expect a Chinese landing on the moon within about a decade. There is a plan. There is a series of processes. There is plenty of money. I think it'll be like the Apollo missions. It will be a land, spend a little while there and come back carrying a bag of moon rocks. And the benefit is really that you get the moon rocks back. So while robotic probes are amazing, there's an awful lot that my planetary science colleagues can do once you get material into a lab. And the best way to do that is to go there and get it. It's much easier than reducing your lab to something that can fly on a spacecraft. We've also, people forget, I think, that we've only been to 6 places on the moon, all of them on the near side, most of them in lowlands. And you can imagine trying to understand Earth in all its variety by visiting 6 places for a couple of days each. So I think there is real scientific impact, even if people are going because they want the Chinese or American or European flags on the surface. There's obviously a lot of interest in going to Mars. Commercial companies like SpaceX are making a lot of noise about the fact that they want to eventually go there. I'm a big fan of Elon Musk's statement that he wants to die on Mars, but not on impact, which I think is quite good twice. Do I think we should go? I'm in 2 minds about this. I would love to share in the adventure of watching people try and reach so far from our home planet and explore. I would go myself if anyone particularly wants to pay me. I don't intend to put in any of the training or effort, but if somebody wants to take me to Mars tomorrow, that would be great. I'd even go if it was a one-way ticket. But I think Mars is a fragile environment. It's possible that there is still life or was life on the surface of Mars. And at the minute, that's relatively uncontaminated by us. And I certainly start to get twitchy when we think about colonies of rich people hanging out for a holiday before we've had a chance to scientifically explore. So my preferred option would be to get Elon Musk and Co to pay for it, for them to go to Martian orbit and then stay on Phobos or Deimos, the moons. And then you can have a lab there and control spacecraft on the surface with a joystick, much more than we can from Earth, and do the scientific exploration that way. But I think what will happen is people will go for the adventure. But I suspect that's still 20 years away.
Thanks, Chris. Does anybody else have any thoughts on this? Not seeing any, so I'll move on to the next question. So again, this is not so much a general question, but not one that I know how best to engage with. Again, maybe this is actually best answered by Chris. Apologies for this, Chris. And Doug asks, what role do amateur astronomers still have to play?
So I think there's a reasonable sense that people for decades have been saying that amateur astronomers no longer contribute useful things to astronomy, and they're always wrong. So just to run through very quickly the different types of amateur engagement. Lee's already mentioned sort of using data, particularly from planetary missions, to create new visions and to coordinate camera activity. There's a camera on Juno that's more or less directed by the team in association with online citizen scientists. We have a bunch of people sorting through data on Zooniverse, but there's still a role for people with telescopes. Michelle will know more about this, I suspect, but there's some deep imaging that amateurs are able to do that brings out fine detail in galaxies that no one else can do. And routine monitoring of the planets, which Lee will know about, is also still mostly done by amateur astronomers. There are still some discoveries made as well. Comet Borisov, for example, which was the first large interstellar visitor. So it's a comet from another solar system, was discovered by a Russian amateur astronomer who got his name on it. So there are things that people can do, certainly online and even with a small telescope.
Yeah, and I think just obviously a lot of the amateur astronomy community are really engaged with promoting and supporting astronomy, and so encouraging new students to become professional astronomers just through all those engagement efforts is really, really important. And just kind of sharing the wonder of our universe with as many people as possible, they have a really crucial role. There are many, many, many more amateur astronomers than there are academic astronomers in the country, so they do have a really crucial role there as well.
They also ask brilliant questions, as we're discovering. So you should, people should also keep prodding us with annoying and difficult questions. That's the go to find out more. But both Michelle and Lee were waving, so maybe they want to come in.
Michelle?
I just wanted to follow up on the monitoring of the planets, because there's a whole army of amateur astronomers out there who are looking at the planets on a nightly basis, and because they're able to do that with the vast investment in time and kit and capabilities that they have, they're often the first to make discoveries. And just right now on Jupiter, for example, there's an enormous eruption of plumes and clouds, which is evolving on an hourly basis, not just day by day. And so by having this army of amateurs across the globe who are taking observations, taking video, taking multi-wavelength observations, and feeding this to a centralized database, that is an absolute treasure trove for those of us who are interested in studying meteorology and climate on other worlds. And we simply couldn't do it. We couldn't do it without the time investment from those amateur astronomers.
Yeah, and I would just say that I work actually in a lot of projects where for probably the last 10 years, amateur astronomers have been providing the best science images for those projects, specifically things like studying the outskirts of galaxies, so not where all the stars are in the middle, but their sort of outer stellar halos, looking for signs of previous small merger events, which tend to show up as beautiful streams of stars. And they're really hard to image because they're so much fainter than the main galaxy. And working with people like David Martinez Delgado, who is a professional astronomer, but he has huge ties to this amateur astronomer community. And he's been producing they've been producing with him, these fantastic images that really have shown us the sort of range of different types of mergers we can see in nearby galaxies. And I would say the professional field's imaging capabilities are only just beginning to catch up with that. So, we call them amateurs, but I think there probably should be a better name for that.
You just stole my point there, Michelle. I was going to bring up exactly that. I think many of the amateur astronomers that I've met are much more capable of using a telescope than I am. Partly this is because I use space telescopes instead, but I think we do need a better name.
Sorry, I also wanted to put in a word from my colleagues who work on variable stars, because these variable stars, they go through flaring episodes, and many of them do need regular monitoring, the kind of time series data that Lee was talking about, but for individual stars. One of the reasons I'm mentioning it, though, is because I know Steve and I both use Hubble data, and one of my colleagues relied on an amateur to help save Hubble because he wanted to target a bright variable star in the local universe with Hubble, but could only do it if he knew it wasn't in a flare within a couple of hours of the scheduled observation. And the only person on the planet who could get him an observation at that precise time that would ensure that Hubble was safe was a home astronomer.
I should put because they'll email me if not, but there are people who look for near-Earth asteroids as well. So a lot of the people keeping an eye on asteroids that might one day hit us or which might suddenly be discovered they're heading our way are amateur astronomers who feed into the same databases that the professional data does. So I think that's basically all of astronomy, more or less, and there's still plenty for people to do.
I do wonder, is astronomy the science which has the kind of almost the widest reach in terms of people participating in it via things like the Zooniverse projects, but kind of more traditional amateur astronomy as well? Is there any other science which is
the
close?
other place that's close or probably beats us is ecology? Yeah. So think of millions of bird watchers and people doing that sort of thing. So it's close, but all of what's common is that those sciences, meteorology, geology, have this legacy of sort of mostly in this country at least, mostly 19th century amateurs who invented data collection and analysis for those subjects, and a lot of that still carries on.
Yeah, that's great. Anybody else want to say anything here? Okay, so the next question is a follow-on from the question that Tim answered, but I think it might be better answered by Michelle, actually. So this is from Stephen, who says, Tim's answer for colliding galaxies included the interaction of gases, but what about the dark matter? Might we speculate that that too should interact?
So the interesting thing about dark matter is that it doesn't actually behave like the gas. It behaves much more like the stars, which gives us some idea of what type of thing dark matter should be composed of. And a really good example for us knowing this is actually the study of a sort of colliding clusters called the antennae. Is it no, the bullet cluster? Sorry, too many clusters. That probably is better for Tim, that question. But yeah, so there's this beautiful system of clusters. So two clusters of galaxies that sort of collided with each other and are now sort of moving away from each other to the other side. And if you image where the stars are and where the gas is, you find that they're in two different places. Because as the two clusters collide, the gas collides with itself, so it cools down and it sort of gets left between, sort of pulled out of each cluster, and you find the gas between the two clusters of galaxies now, and then all the stars are sort of separated from the gas a little bit. Now you can then also measure where most of the mass and where most of the stuff in this colliding set of clusters lives, and that can tell you a lot about what you're looking at. So if the clusters were only made of stars and gas, then most of the material should be in the gas. So if you use gravitational lensing, yeah, this is the image here. If you use gravitational lensing, you can measure the mass distribution in this cluster. And you should find that if it's only coming from stars and gas, that most of the mass should live where that pink stuff is in the center of these two colliding clusters, whereas all the stars lives in the blue portions instead. Because there's more gas than stars, there should be most of the mass living in the center of that collision. But what the lensing results actually show is that most of the mass is found where the stars are, so away from the gas. And so it's moving with the stars, and we think this is one of the sort of key pieces of evidence for dark matter, because there's way more stuff there than we would have thought if we were only considering stars and gas. Hopefully that was a reasonable explanation to the question.
Yeah, thank you, Michelle. And you should all thank me for getting that image up really, really quickly. If a couple of seconds more. Because I was doing that, I didn't look for my next question, but there is one question here which is not aimed at one of the panel members, but it's actually aimed at Sandra. So obviously I saw Sandra have to jump then. obviously this pandemic has had serious negative effect on the funding of the Herstmonceux Science Centre, but what, if any, will the lasting impact be?
That's a good question. I'd like to be able to answer that, but who knows what the future's going to hold at the moment. But we are so pleased that people have come back with all, we've had full days pretty much since when we opened. What we are looking forward to, what we're getting asked an awful lot is, when's your next stargazing evening? And I'd love to be able to say a date, but of course that's a real sticking point. So if anybody's got any real ideas, I've got a grant in at the moment for getting the camera attached to one of our telescopes. Obviously they're historic telescopes, so we don't want to not use them anymore. So I'm going to have sort of hopefully live images through a screen. Everybody wants to put their eye to a telescope. Well, we can't do that at the moment. And we've got, if anybody's been here, you know that there's steep, narrow stairs up to small domes as well. So that's another sticking point. But we are trying hard. We're going to get lots of different opinions about how we're going to go ahead with it, but we're not going to stop. We are going to try our best, because I was going to jump in on the amateur astronomy thing, because we have a lot of our STEM ambassadors who are also amateur astronomers, and they are a huge and fantastic link between the general public and professional astronomers. I'm not saying you are scary guys, but you know, sometimes you're not as accessible, and you can access, general public can access all the astronomy through the amateur astronomers. So and which is great. So keeping our fingers crossed. We are, you know, we're still here. We're still going to carry on, and we are going to be opening the telescopes and doing stargazing evenings as soon as we possibly can.
Sandra, there are about 77 people watching this live, and lots of people I hope will watch later on. How can people help you? In particular, how can people send you small amounts of money that might help right now?
We are on our webpage, that's of the Astronomy Festival webpage. We've got a crowdfunder button. And if you can go along to the crowdfunder button, and if you are able to donate anything, we don't get any external funding at all, and our Astronomy Festival was our biggest fundraising event of the year. So if you are able to do that, we'd be so grateful. Thank you very much. I get very emotional when I see this panel of astronomers in front of me. It's just an amazing thing that's happening today. I know you can't be with us, we can't see you. There's an awful lot of people come back to the festival year on year, and they've become our friends as well. But if you can, please go to that crowdfunder page and donate what you can. We would be so grateful. Thank you.
Hopefully next year all the panel can be there in person with everybody else as well.
Yes, please. Yes, please. You are all invited, of course.
So we're approaching about the last 15 minutes now. So people, if you do have questions, then please do post them in. One good point has been made here by Jay Brand, and I had no idea that this was the case, that apparently the word amateur literally means somebody who loves their subject. I had no idea that was the case. And so obviously we should be continuing to use that term, but really convincing people to use it to actually know the actual meaning of it. So it's amazing that I've learned something. That's fantastic. Okay. Oh, wow. This is a question from me. So this is really exciting. This wasn't a plant at all. This is really directed at me. Actually, maybe Elizabeth as well. This is from Charlie. So I only just saw this question, which is why it excited me so much. And the question is, what is the largest observed redshift for a galaxy? And how much further will we be able to look with the James Webb telescope? Okay. So just to answer this question, redshift is a way that we can work out the distances to objects. It's something that's relatively easy to measure for distant galaxies. And we know that there's a correlation first measured by Hubble that links redshift to distance. Now, added onto this, we also have the fact that the further away an object is, the earlier in the universe's history we're actually seeing that object. Okay. So today the record holder is about a redshift of 10, but that doesn't really mean anything. What a redshift of 10 really means is that we're seeing a galaxy or a different object when the universe was only about 500 million years old. compared to its current age of around 14 billion. Now, this maximum number, this 10, this was measured by Hubble, and it really is the biggest number that Hubble could ever measure. And that's because the light from more distant galaxies gets shifted progressively into the infrared, where Hubble can no longer see it. And so the thing that's going to change this in the future is the James Webb Space Telescope. James Webb extends much further into the near infrared. Okay, it's a much larger telescope, so it can see many fainter objects. As to what is the highest redshift that it's going to see, we actually don't know that answer because we don't have a very good model for how many galaxies and how bright the galaxies are in the very early universe. So we do have models for it, but lots of the models disagree with each other. And so it could be that we find something at redshift 15, could be we find something at redshift 20. If we're getting to around redshift 20, we're talking only a couple of 100 million years after the Big Bang, and we might really be seeing the very first generations of stars and galaxies to form in our universe, which is one of the things that, obviously, because it's my field, I'm really, really looking forward to. While I look for another question, Elizabeth, do you have any thoughts on this as well?
Certainly, yeah. Redshift tends anything at redshift 15 or 20. It's harder to say.
We lost you a little bit there as well, but I think you kind of concurred with my answer if I got it right. Oh, we seem to have lost Elizabeth again. We have another question for Chris here. And this is that during lockdown, have you actually seen an upsurge in people signing up for things like Zooniverse?
Yeah, we've been busier than ever. So the way we think about this is our normal record came when we used to collaborate with Brian Cox on the Stargazing Live programs, and he'd stare into the camera and tell his audience to come and help us out with our various projects, and that was a big deal. Every day was like that for a few months in March and April, and it's been busy since. So we know why that is. We think that some people who do have spare time in the situation that we find ourselves in, I really appreciated the ability to contribute to something, like to collectively do something and try and think about space and not about whatever was going on here on Earth. So it's been really heartwarming and exciting to see that. But there's plenty of data left. Our scientists have put more projects together, and I hope people will be able to dig in whenever they can.
Great, thanks, Chris. This is a question for Joe. And again, related to the James Webb Telescope, but how will the James Webb Telescope help in detecting exoplanets? And this is from Theodore.
So James Webb won't really detect exoplanets. It will do better than that. So it will allow us to look in detail at the atmospheres of planets that we already know exist. So the kinds of spacecraft that are designed to detect exoplanets operate differently to James Webb. So they are things like Kepler, which is now finished, and the current mission called TESS. And what they do is they pick a single but quite broad band of light to look in, and they collect all the light, all the photons within that band, and they measure the brightness of a star over a period of time and look for dips in that brightness that would correspond to a planet passing in front of the star. James Webb can view these events as well, but instead of just looking at a single wavelength or a single band of light, it's going to look right from the very reddest end of the visible, as Stephen said, all the way into the infrared and much further into the infrared than Hubble can access. And what it allows us to do is to split up that light into its constituent wavelengths or colors. And specific gases that might reside in the atmospheres of these planets absorb sort of fingerprints of different colors of light. So we can identify them based on which colors appear to be missing more when the planet passes in front of the star, because some of that starlight will be filtered through the edge of the planet's atmosphere. So we can already do this to an extent with Hubble. We've detected water vapor, for example. Chris already mentioned that in the atmospheres of virtually every planet we've looked at, actually. Water vapor is pretty much everywhere. But with James Webb, we'll be able to look for different molecules that we can't currently access with Hubble. And one of probably the most interesting of these is ozone. So we have ozone in our atmosphere. It's 3 oxygen atoms stuck together. In our atmosphere, it resides in a layer about 10 kilometers above the surface, and it's created when common or garden oxygen, 2 oxygen atoms stuck together, gets hit by some ultraviolet light, breaks up and reforms in a different way. And if we see that in the atmosphere of another planet, it would be a good indicator that the atmosphere has quite a lot of oxygen in it, which is interesting to us because that could be an indication that there might be something putting the oxygen there, i.e. something living. It wouldn't be an absolute smoking gun, because there are other things that can put oxygen in an atmosphere, but it would be very, very interesting indeed.
Excellent. Thank you, Joe. Yeah, you were hesitant to say the word, but I'll be honest, aliens. We're all after the aliens, right? Great. This next question is one for Lee. So this is from Gemma, who asks, why are there so many moons around the gas giants, but relatively few in the inner solar system?
That's a really great question. And in fact, people have been trying to explain the architecture of our solar system through numerical simulations where they put the various ingredients in the right place and then let it evolve via gravitational interactions for many years now. And the challenge has always been, how do you go from small rocky sort of seeds of planets to the kind of planets that we then see in our solar system? And the piece of the ingredient that really helps in terms of having a lot of material in orbit around the giant planets is the presence of something called an ice line. That is, when the sun's effects are heating up the inner part of the solar system and only allow rocky material to exist close in, whereas in the outer solar system, it allows ices of things like water, things like carbon monoxide, even ices of nitrogen to exist out at great distances. And that provides the seeds you then need for the giant planets. The giant planets then act as their own seeds for pulling together material from their surroundings, opening out rings within the disk as they're forming. And all that detritus, all that debris from the formation of the planets then allows satellites to form. The big problem is that we don't really know what the insides of a lot of these satellites are like. Okay, we have broad brush estimates of it's got so much ice, so much water, so much rock, and that's blended together in different proportions depending on how deep you go. But what we can't do is go and sort of thinly slice up these planets to find out exactly what they're made of. For things like Jupiter and Saturn, because we've had missions there, we've got a fairly good handle on the proportion of rock and ice within their interiors. But go to somewhere like Uranus or go to somewhere like Neptune, where we've only had that single flyby mission by Voyager 2 back in the late 80s. And we really don't have a great handle, not only about the satellites, but also what Uranus and Neptune are really made of. And that's a key missing ingredient in this puzzle of figuring out how planets form and how their satellite systems form. Crack that puzzle, and we'll be able to apply that knowledge to some of the distant extrasolar planetary systems that Joe has been talking about.
Thanks for that, Lee. And I just want to pick up on one word that you said a few times then, puzzle. Lots of people think that maybe physics and astronomy, it's all been solved already, but hopefully this Zoom session has kind of showed you all that there is still a tremendous amount for us to do. There's a tremendous amount of work out there for astronomers to do. So astronomers and physicists and other scientists are as relevant as ever. There are mystery after mystery. If anything, as we look deeper and deeper at the universe, we never actually end up. We do answer some questions, but inevitably we always find more questions than we've actually answered. And I do wonder sometimes whether it's just some kind of big cosmic joke that the harder we dig, right, we never actually get down to the bottom. But it's fun as well. It's always nice to have questions.
I think that puzzle aspect of it, that problem-solving aspect, is something we try to emphasise to our students at Leicester and across the UK. That what we're doing is providing you with a toolkit: the maths, the physics, the chemistry, hopefully some of the biology, but also the computation and software design. And what you do with that toolkit is then up to you. But when faced with a problem in cosmology or gravitational astrophysics or planetary science, you've suddenly got that background of tools that you've learned to apply to one of these great puzzles that are out there. And it's often a surprise, even even to us, when you come up with an answer to something, having used all these tools. But that is one of the reasons that I love this job so much, is because you can surprise yourself with what you figure out by looking at the data.
Yeah, I mean, it is a fantastic job. And I know there's lots more questions on careers that I'm going to try and answer another one of them before we end. One more kind of science question, and I'm actually not sure who best to direct this to. Maybe Elizabeth, maybe Michelle, maybe both of you can chime in. And this is from Tim, who asks what the panelists' views are on Betelgeuse about to go supernovae, and what might we expect to see if it does?
I think the consensus is that it's very unlikely Betelgeuse will go supernova anytime soon. It's a very massive, large, red, very variable star with huge convection cells on its surface. So big changes in its light over time. And while it's been going through a dip, it is now coming out the other side of that dip. And it's been extreme, but not beyond what you might expect for a star of that type. So while Betelgeuse might go supernova anytime in the next 10,000 years or so, there's no more reason to believe it will be tomorrow than in 10,000 years' time.
Thanks, Elizabeth. Michelle, do you have anything to add there?
Only if it were to go supernova, it would be super cool. So I think that was one of the reasons astronomers were so excited. That we kind of knew it probably wasn't going to go, but everyone was just clinging on to that idea that it might do. And because it was going to be so bright that, you know, the explosion you should be able to see actually during the day in the sky, not just at night. So that would be like mind blowing. And we learned so much cool stuff from actually watching something go supernova nearby. So I think that would have been cool.
I surprised myself and decided I didn't want it to go. When it was fading, I was so freaked out by Orion looking different. And maybe this is growing up looking at the sky. I found it deeply disturbing that Orion had changed. And I was relieved to see it. It happened sort of just as we were locking down, and just seeing Orion come back made me sort of feel that the cosmos was all right. So I don't care what we plan. I want Betelgeuse to stay there. But I understand that if you study supernovae, that's probably not your attitude.
Well, I mean, I don't really study those, but I also was just really excited that I got to show people like astronomy, like stars changing in real time. Like that was actually for me like a big. Yeah. A lot of my friends who don't normally ask me many questions, they had me pointing out Orion every time we went out in the evenings, and it was just cool. Being able to see that the star was noticeably less bright and compare it to another star that it used to be brighter than, and that was a really amazing time actually. So I really enjoyed it getting dimmer.
So this is where I convince everybody that I'm not a real astronomer, but is Betelgeuse one of the shoulders of Orion?
Yeah, the name, a loose translation of the name is armpit of the Great One. So top left.
Ah, I was right. That's amazing. So maybe I'm a real astronomer. Fantastic. So we've had loads of questions about careers. So I think I just wanted to end on one of those, because obviously part of our job and part of the reason why we're here today is to encourage the next generation of astronomers and scientists and people who are going to use these skills. So I was just hoping that maybe Tim, because you haven't answered a question recently, whether you can just give a quick overview of your career and what are the kind of stages in becoming an astronomer?
Yeah, okay. So I think the first thing is, if you want to become a professional astronomer, you probably need to go to university to study physics. That could be you did it straight out of school. It could be you go back and do it, but that physics is really what you need to know. You could do that as part of a direct astrophysics course, or you could do straight physics like I did. Really, they're going to teach you the same tools, which is how you mathematically analyze the universe and have that background that you need, and also the computational skills and the skills about how to think about those type of things. So that's sort of the first stage. If you go get that background in the physics. So then after that, the traditional path that leads to going into astronomy professionally is you need to do a PhD. So you find a university somewhere with someone doing research that really speaks to you. And a PhD is not the same as a normal degree. It's a labor of love in a way that you have to be really into what you're going to do. You don't want to take something just because it was the one thing you're offered. If you don't care about it, because you won't succeed. You have to care about what you're going to do. So you need to find that opportunity, and there are PhD positions available at universities all over the country and all over the world would hopefully do that for you. So that's typically, in the UK at least, it's 3 to 4 years of study, doing your own research, publishing in peer-reviewed journals until you get that PhD. Then you become a doctor. So then after that, typically for most people, you'll end up getting work experience in places around the world. So you may go out, spend 3 years somewhere else in Europe, somewhere in the US, could be in Asia somewhere, Australia. Really, there's many opportunities in Africa. So often people end up going abroad. They don't have to. You can also have professional astronomers who spent their whole career in the UK also. So you would typically do, on average, maybe 2 of these type of postdoctoral positions, we call them. And then hopefully if you're lucky and you're doing great work and everyone appreciates that, then you can get a position at a university and an observatory where you can, you have that sort of job security and you can run your astronomy career alongside either teaching the next generation in the university or helping run telescopes in the instance of an observatory. So those are the sort of very traditional routes to doing it. But as was mentioned earlier, I think it's important to say that we don't just need more people like us. The whole industry around astronomy and space needs people with so many different talents. We need people who can organize events like this to reach out to the next set of people. We need software engineers. We need project managers, all of these different types of skills. Whatever you're good at, it's actually needed somewhere in this whole industry. So you don't have to go down this traditional route if that's not for you. There are other ways to be involved as well.
Thanks, Tim. That's a great answer. So we're just past the 3:30 mark. So I think I set this to be 90 minutes, or at least that's what I told the panel. I'm just wondering, do any of the panelists have any additional thoughts while I just share something? Anybody have anything to say? So all I was going to share, and hopefully this is now working, hopefully we can all see this, is just some other events which I've identified that are coming up soon. So I've been very selective in these events, mostly because they're either in Sussex or they have involvement from people in Sussex. But I organise a series of online lectures called Sussex Universe, which isn't actually just astronomy anymore. It's everything that the University of Sussex does. But our next lecture is an astronomy lecture, which also features a live Q&A. So you can get the opportunity to, again, join via Zoom and actually ask the speaker some questions after watching their talk. And then we have the National Astronomy Week, which is taking place at the middle of November this year. This is focused on Mars. Now, this will also feature a live Q&A, and I think some of the panel members here will be returning for that. I think that live Q&A is going to focus specifically on whether there is life in the universe. And then the Royal Astronomical Society has been organising online talks over the last few months. I know myself and Michelle and maybe others have been given some of these talks as well. And there are countless opportunities on the internet via YouTube to learn more about astronomy and to engage with astronomers. And so I just wanted to mention that and just thank the entire panel again, and obviously Sandra for facilitating today. And just, yeah, thank you everybody for the time, and thank you everybody for your excellent questions. It was really, really fun to answer them. Do you have anything else?
I just want to say thank you so much for all the panelists for giving up your time today. It's been really good, excellent. I think it's been really engaging. Fantastic questions, fantastic answers. So thanks very much. And again, thanks to all our participants who've logged in, and I hope you know, you've had your questions answered. Sorry if you haven't had your questions answered, but you know, these things go, it's just you know, time constraints. But thanks again for supporting the Astronomy Festival. Hope to see you back at Herstmonceux in person next year. I mean, as I say, if you are able to donate, do go to the crowdfunder, please. But thank you very, very much for attending today.
And just one final comment from me. Is it aliens, Chris? Oh, he didn't blink. Oh, damn. Yeah, I was really hoping it was aliens. Okay, thank you everybody for listening.
Thank
Apologies
you,
that we couldn't answer every question. But yeah, it was great to answer all your questions. And have a good rest of your weekend, everybody.
Thank you very much. Thank you. Bye-bye.
Bye, everybody.
Thank you, everybody. I've stopped recording. I've stopped live streaming.
There are still people watching though. So
yeah, there are still people watching. But
thanks
thank you
for organising that, Steve. That was cool.
Yeah, thanks, Steve, for organising that. That was excellent. I hope everybody enjoyed themselves.
And apologies for my dodgy internet connection.
No. It's amazing. My internet connection didn't go down, but no. But thanks very much. Okay, well, I shall end it there. But thanks, everybody, and hope to see you at Herstmonceux sometime in the near future. Take care, everybody.
Nice to see you all.
Bye-bye.
Nice to see you all. Bye-bye.
Hello, my name is Tom Kurz.
My name is Edward Bloomer, and we're astronomers at the Royal Observatory in Greenwich.
And this is the Astronomy Photographer of the Year 2016 Planetarium Show. We're going to be taking a look at images from the shortlist of this year's competition, and we begin with images of the Aurora, in many cases the Aurora Borealis or Northern Lights, which are the most popularly captured subject in this particular category. And here we can see an image of the Aurora overhead, beautiful colours, green and pink, captured, these colours both characteristic of a very active and dynamic auroral display. So while we enjoy the Aurora dancing overhead, we'll take a look at some more images, and this one coming from Kolbeinn Svensson. And this image captures several auroral curtains which are very sharply defined. In Norway, Bernt Olsen was just a couple of miles outside of Tromsø when he captured this image of the lights once again overhead. Here we can see the shape of the curtains as they appear coming overhead as rays. The aurora actually appears about 80 miles or so above our head in the upper part of the atmosphere, never reaching that close to the ground, but from directly underneath it feels like it's all around you. And not all photographers capture the northern lights. In this picture, we see a photograph of the southern lights, or Aurora Australis. And this image is very interesting because of the background subject as well, not just the Milky Way, our own galaxy, but two popular objects that you can see from the southern hemisphere. Clearly, the Magellanic Clouds, the large and the small Magellanic Cloud. The high altitude of the aurora here reveals a pinkish red color, which is characteristic of high altitude oxygen.
In the show, we wanted to take you on a bit of a journey. So we're going to fly out towards the sun, which is, of course, the cause of the aurora. And we're going to take a look at some solar astrophotography, which is rather specialised even within a somewhat specialised subject. The sun is, of course, far too bright to view without a great deal of care and attention. What we have to do is we have to filter the light of the sun. But done correctly, you can see the power of the sun, and you can see details that are just impossible to look at with the naked eye, which is, of course, a very dangerous thing to do.
Images of the sun are often captured in black and white using special filters which just isolate one particular colour. So we've seen a hydrogen alpha image that shows us the sun's lower atmosphere, the chromosphere, and here this detailed image shows us the dynamic nature of this part of the sun. its magnetic field sculpting the gas into these beautiful structures called filaments. When these structures are seen on the limb or the side of the Sun, they are viewed as prominences. But it's also possible to look closer to the Sun's surface in good detail if we select a different wavelength. And whereas hydrogen alpha is part of the visible red spectrum, an alternative wavelength would be the calcium K line, which is actually part of the deep violet spectrum. In fact, it's so close to the violet spectrum or ultraviolet spectrum that some people can't actually see it with their eyes.
What's amazing about taking pictures of the Sun is that because, of course, the Sun is such a dynamic surface, as well as the atmosphere, every image is different. Every image is going to capture something slightly unique.
So moving from hydrogen alpha to calcium K, instead of looking at the Sun's lower atmosphere, we're now looking right down onto what we might call the fluid surface of the Sun. So rather than seeing the results of magnetic storms, we're actually looking pretty much directly into those storms, and we see them as sunspots, these dark features on the surface of the Sun surrounded by bright areas of crackling activity. These are very magnetically active regions of the Sun's surface, and this particular wavelength, which is often invisible to our eyes, can still be a delight for some viewers, and it's very, very easy to capture with the right filters. But this image again will have been taken in black and white. The violet colour has been added by the photographer for artistic effect.
Different physical processes produce radiation at different wavelengths, and so looking at one particular set of wavelengths or one small part of the electromagnetic spectrum means that you're missing out on a huge amount of information that is available. One of the skills of the astrophotographer is to select their wavelengths and to present you something. There is an artistic and an aesthetic appeal about some of these images, and what we're about to see will really highlight that.
Scientists use professional equipment, of course, to isolate different wavelengths, to look at the sky and see different properties. It may depend on which sort of objects they're looking for, and perhaps they want to look at different energies which may be outside the visible part of the spectrum. But increasingly, amateur astrophotographers are also getting access to this equipment, perhaps, for example, using robotic scopes, which can be kitted out with near professional grade equipment. So one robotic scope image submitted to the competition this year is Iridis, and this image reveals two planetary nebulae. These are the results of stars which were once like the Sun but have since died. At the top we see the Cat's Eye Nebula, and below it the Ring Nebula, a very popular summer object. And we can actually see the differences between these two nebulae by separating the colours in the visible spectrum, which the slitless spectrograph on the telescope has done here. For example, in the Cat's Eye Nebula you can see more blue and violet emission, suggesting that this is actually hotter at the core than the Ring Nebula, which is more mature and has since cooled down.
Not all of the colour in an image is due to specific filtering. Here we have the refraction of the atmosphere causing Sirius, the star Sirius, to appear in a huge variety of different colours. Taking a video of Sirius, the photographer actually separated out all the different colours that he was able to see in individual frames. Sirius appears to flicker quite noticeably. It's a really good target for amateur astronomers because of that.
And the photographer Steve Brown deliberately defocused the star to spread the colour out into a disk. And this is actually a really good method if you're looking for colourful stars yourself, to see the colour more prominently. So the atmosphere produces numerous effects on our observations, and of course for most of the history of astronomy, astronomers have had to tackle Earth's atmosphere before the age of space-based telescopes. Nevertheless, ground-based telescopes are still useful today, and here we see the atmosphere itself along with the Haleakala Observatory as a really beautiful photographic subject. So this is more about the human impact on astronomy and also the sky that we have to tackle. And while modern instruments like this one are still operated around the world, historical instruments are still used as well, usually in a different capacity for public viewing. We have our own large telescope here in Greenwich, a 28-inch aperture refractor dating from the late 19th century, and this is still operated throughout the year for public viewing events. We also do our own astrophotography with it, and we have colleagues around the world who are doing this too, for example at the Great Lick Refractor in California, and here we can see a photograph of a public event inside the dome. And this is a great astrophoto because while we can see stars outside the dome, we can also see people taking part in looking at the stars with this lovely historic instrument.
As we can see in the time lapse here, the telescope needs constant readjustment as the sky revolves around our heads. So if we want to keep something in view, we're going to have to keep moving the telescope. Using this, we can actually get some interesting effects. Here, star trails are created by the Earth's rotation, and a long exposure will trace out the paths of the stars throughout the night. We can also see the streak of a meteorite, creating a sort of hand of a clock effect. This is an amazing image because it's so well balanced. We're getting the dark sky and we're getting some bright star trails, but the photographers also managed to balance out the bright lights of the city as well.
So while we astronomers are always trying to overcome the rotation of the Earth, the photographer here has used it to his advantage for this photograph. Now the sky in Greenwich is unfortunately not as it once was, but you can still go out to dark sky sites around the world and get beautiful views of billions of stars making up our Milky Way overhead. Greg Stevens in New Zealand has such a view captured here, 33 individual photographs stitched together, producing this extraordinarily high resolution image, which we put over the entire dome, so your eye can be drawn up there to the bright center of our galaxy, right overhead.
While some astronomers want to take as wide a field of view as possible, what we can also do is we can zoom in and we can look at something much more specific. So here we're looking at the Large Magellanic Cloud, one of the dwarf galaxies that is gravitationally bound with our own. And this is an amazingly high resolution image. We can see lots and lots of detail.
The Large Magellanic Cloud and its cousin, the Small Magellanic Cloud, are really beautiful sights that you can see from down south. And one of the highlights in these two clouds is the Tarantula Nebula right here in the Large Magellanic Cloud. And we're getting a bit closer to it here, courtesy of Christopher Clayton from the UK, who took this photograph in Australia, a perfect place to go looking for this one. And the Tarantula Nebula is one of the largest and most active known star-forming regions in any galaxy in the local part of our universe. It's much more massive than any of the nebulae local to us here in the Milky Way, and there are thousands of young stars being born in this galaxy, even as you watch this show. So we're going to imagine a young star cluster being born in the LMC or any star-forming nebula, and this could be a great photographic subject. So let's go inside a nebula and compare it to one that's a little bit closer to us here in the Milky Way.
So I think that many people are unaware of the fact that stars have a lifespan. They are born, they live and they die, and they're born in places like this. This is the Lagoon Nebula, which is a star-forming region, and it's home to Bok globules, which house the young protostars. The eventual fate of the star will depend on a number of local conditions, as well as the mass of the star itself. Some come to a rather gentle end. Again, as far as stars are concerned, for humans, they tend to be pretty violent things no matter what you're thinking of, but some of them come to a catastrophically violent end.
Stars born inside nebulae like this one have access to a lot of material. They can be very greedy and they can grow to become the sorts of stars that live fast and die young. And when they do die, they are very spectacular. So we're going to imagine such a star approaching the end of its short life. And when a massive star begins to die, it will first swell up, becoming a red giant as it begins to get hotter and hotter in the core. Eventually, it will actually run out of fuel and the core can collapse, creating a shockwave known as a supernova. And while supernovae are incredibly short-lived and difficult to capture, what they leave behind can be very beautiful. So we're now looking at a supernova remnant from a star that exploded thousands of years ago. This is part of the Veil Nebula in the constellation Cygnus, and this particular part is called Pickering's Triangle, and it's one of the less frequently captured areas of this nebula. So it looks really delicate, but it actually tells us of an extremely violent past. We're seeing a shell of gas expanding into the galaxy, and as that hot gas collides with other material in the interstellar medium, it becomes hot enough to glow.
One of the most important processes that's going on in a supernova, as far as we're concerned here on Earth, is the heavy element nucleosynthesis. So it's in these supernova that the gold, the silver, the lead, the uranium, all that sort of stuff, the heavy elements are produced. So the stuff that we have on Earth like that is produced from an earlier generation of stars going novae.
And these elements, of course, are found in our own bodies and were generated by exploding stars. Here in the remnant left behind in Vela and Puppis, who knows what kind of gas may one day rain down on a new generation of worlds.
And from an artistic point of view, one of the most important things for the astronomer is to choose the colours. Because they have specifically filtered particular wavelengths, they have to decide on a colour palette, and they have free choice if they want. So you can get the same picture, but with radically different appearance.
By selecting a colour palette like this one, the photographer's chosen to bring out a sort of different style and level of detail in this part of the California Nebula. These enormous structures in our galaxy and beyond remain pretty much unchanged throughout our short lifetimes, but there are transient or short-lived events that you need to capture with very careful planning. Felipe Jacot took a photograph of the Earth's second largest satellite, the entirely artificial International Space Station, where a crew of astronauts and cosmonauts work on numerous science experiments as it orbits the Earth every 92 minutes. In this photograph, you can see the trail of the International Space Station, captured over a very long exposure, and rather wonderfully, it passes, or appears to pass, very close to 3 planets there, Venus, Jupiter, and Mars, high up in the sky, as seen from France.
Another image that was anticipated, very carefully planned for, and the location scouted out previously, is this image where we have Mercury, Venus, Mars, Jupiter and Saturn, as well as the Moon, up in the sky at the same time in just the right position. Here we're looking towards the Matterhorn in Europe, and this really is only possible on the 6th of February 2016. The photographer speaking to us later on told us that the night before was rainy, so this was the only chance he got to actually take this picture, and he'd planned it out beforehand using a mobile phone app to make sure everything was going to be in just the right place at the right time.
We have a much closer view of a couple of these planets to enjoy, courtesy of Damien Peach, a world-class astrophotographer from the UK. Here we are immersed in Saturn's rings, which are composed of chunks of ice and even snow travelling around this gas giant world, about 1 billion miles from the Sun. This ground-based image from Damien captures the rings in extraordinary detail, and also behind them the storms there in Saturn's cloud tops, including the very famous hexagonal polar vortex surrounding Saturn's North Pole, a remarkable 6-sided storm which is around 2.5 times wider than our entire planet. This picture really is extraordinarily detailed, considering it was taken from so far away here on the ground. And not content with this incredible image of Saturn, Damien has also turned his telescope to Jupiter, the largest planet of all, even closer to us, of course, and therefore even more detail can be seen, including the Great Red Spot, which is actually shown at the top of this image because it's been flipped by the telescope, but is really part of the southern hemisphere of Jupiter.
The rapid rotation of Jupiter and the ever-changing structure of its upper layers of the atmosphere mean we get a different view of it all the time, and it means that planetary astrophotography, particularly with Jupiter, has its own unique set of problems and indeed solutions. I think this is amazing, and I think the previous one was as well. What I think is great about them is that if you try to convince someone that they were taken with a space-based telescope, I think that could be quite easily done.
Much closer to home and a really popular photographic subject owing to its relatively large size and brightness in the sky is of course our largest satellite, the Moon, and we have two really high resolution views of its surface here.
First we have Tycho, which is very bright, very distinctive, and it's a great subject for astrophotographers because there's so much detail there, and the central framing of the crater really gives an indication of the 3D nature of it.
On the right-hand side, also seen in sharp relief, another view of the lunar southern highlands. From Maurolycus to Mauritius is the name of this photograph, although there are of course many more craters in the photo because there are just so many deep and bright craters near the Moon's south pole.
This picture makes us feel perhaps very young or very transient ourselves. We can see time etched into the geology of the rocks themselves, and overhead the Milky Way itself. The photographer here has brought out colours and detail in both the Milky Way itself and the rocks, so we're getting a very nicely balanced image, but we're also getting a lot of detail that we wouldn't see necessarily with our own eyes.
Some of the things that photographers capture in the sky are actually seen more by their effects. There are tiny fragments of rock and metal and even ice in our solar system known as meteoroids, and these are objects that are due for a collision with the Earth. And when these meteoroids strike the atmosphere, of course, they create meteors or shooting stars. On the left-hand side is a photo of the Perseids, which is seen every year in August,
while the right-hand side is the Geminid meteor shower. And what's happening here is that the Earth is moving into the tail of a comet, and that means that the shooting stars appear to radiate from a particular point.
We've made our way all the way back to Earth, but we're not actually finished, so now we need to jump to a much grander scale, and we're going to go out into the realm of the galaxies.
We are going to take a look at our nearest large galactic neighbour, the Andromeda Galaxy. This incredibly high-resolution, stunning image shows a huge amount of detail, not just within the galaxy itself, and we can see the difference between the spiral arms and the galactic core, but we're also seeing lots of the gas and dust material, the sort of veil of material that exists between us in the Milky Way and Andromeda. Andromeda is actually 2.5 million light years away, but it's closing that distance as it moves towards the Milky Way.
The galaxies come in all different types, and we have two images, both captured by different photographers from Italy, which is very fitting as it is, as many consider to be the birthplace of modern astronomy. On the left-hand side, we can see M82, a starburst galaxy, irregular in shape and extremely active, many stars being formed there. And on the right-hand side is NGC 891. This particular galaxy is a spiral-type galaxy like Andromeda and, of course, our own Milky Way, but it's seen almost perfectly edge-on, so the dark dust lanes in the spiral arms are seen in silhouette against the bright spiral arms and, of course, the central core of the galaxy, one of the brightest parts of all. This is how our Milky Way would appear if we could make the technologically impossible journey outside of it.
The vast distances between galaxies mean that we only get one view of them. It's not going to change over the course of our lifetimes. And what that means is if we want to take a picture, we're going to really need to bring out something special. Here we can see a whole cluster of galaxies. Something like this requires a lot of exposure. In fact, this may be the longest exposure picture taken by an amateur astrophotographer.
Rolf Olsen in Denmark spent 152 hours gathering an enormous amount of truly ancient light to reveal all of these island universes drifting in the cosmos.
And then, as we move back towards our own Milky Way galaxy, we see this wide field around the galactic centre. An incredibly bright image. We can see an astonishing number of stars, but also that really, really delicate structure to the gas and dust clouds within.
This picture is very colourful, and while the colour has been greatly enhanced, it reminds us that there is colour in our galaxy. There are golden yellow regions full of older stars and bright blue spiral arms, and of course those pinkish areas, nebulae, where young stars are being born.
Each year, the Astronomy Photography of the Year competition receives entries from all over the world. We've got them from all 7 continents now, which is rather nice, and we really want to encourage as many people to take up this hobby and enter as possible.
But there can only be one overall winner, and this year the prize goes to Yu Jun from China, who took a series of photos immediately before and after the very moment of totality of the 2016 total solar eclipse seen from Indonesia. This photograph, called Bailey's Beads, captures the phenomenon for which it's named, bright spots of light appearing just around the moment of totality in an eclipse, the last or first gasps of sunlight spilling through the valleys on the rugged edge of the moon.
And on a rather heartwarming note, the photographer proposed to his now wife just after taking this image, and she refers to it as her diamond ring.
If you've been inspired by the images that you've seen in this show, then we hope you'll take part next year, and we really look forward to seeing your images in a future competition. Hello, my name is Tom Kurz.
My name is Edward Bloomer, and we're astronomers at the Royal Observatory in Greenwich.
And this is the Astronomy Photographer of the Year 2016 Planetarium Show. We're going to be taking a look at images from the shortlist of this year's competition, and we begin with images of the Aurora, in many cases the Aurora Borealis or Northern Lights, which are the most popularly captured subject in this particular category. And here we can see an image of the Aurora overhead, beautiful colours, green and pink, captured, these colours both characteristic of a very active and dynamic auroral display. So while we enjoy the Aurora dancing overhead, we'll take a look at some more images, and this one coming from Kolbein Svensson. And this image captures several auroral curtains which are very sharply defined. In Norway, Bernt Olsen was just a couple of miles outside of Tromsø when he captured this image of the lights once again overhead. Here we can see the shape of the curtains as they appear coming overhead as rays. The aurora actually appears about 80 miles or so above our head in the upper part of the atmosphere, never reaching that close to the ground, but from directly underneath it feels like it's all around you. And not all photographers capture the northern lights. In this picture, we see a photograph of the southern lights, or Aurora australis. And this image is very interesting because of the background subject as well, not just the Milky Way, our own galaxy, but two popular objects that you can see. The high altitude of the aurora here reveals a pinkish red color, which is characteristic of high altitude oxygen.
In the show, we wanted to take you on a bit of a journey. So we're going to fly out towards the sun, which is, of course, the cause of the aurora. And we're going to take a look at some solar astrophotography, which is rather specialised even within a somewhat specialised subject. The sun is, of course, far too bright to view without a great deal of care and attention. What we have to do is we have to filter the light of the sun. But done correctly, you can see the power of the sun, and you can see details that are just impossible to look at with the naked eye, which is, of course, a very dangerous thing to do.
Images of the sun are often captured in black and white using special filters which just isolate one particular colour. So we've seen a hydrogen alpha image that shows us the sun's lower atmosphere, the chromosphere, and here this detailed image shows us the dynamic nature of this part of the sun, its magnetic field sculpting the gas into these beautiful structures called filaments. When these structures are seen on the limb or the side of the sun, they are viewed as prominences. But it's also possible to look closer to the sun's surface in good detail if we select a different wavelength. And whereas hydrogen alpha is part of the visible red spectrum, an alternative wavelength would be the calcium K line, which is actually part of the deep violet spectrum. In fact, it's so close to the violet spectrum or ultraviolet spectrum that some people can't actually see it with their eyes.
What's amazing about taking pictures of the sun is that because, of course, the sun is such a dynamic surface, as well as the atmosphere, every image is different. Every image is going to capture something slightly unique.
So moving from hydrogen alpha to calcium K, instead of looking at the sun's lower atmosphere, we're now looking right down onto what we might call the fluid surface of the sun. So rather than seeing the results of magnetic storms, we're actually looking pretty much directly into those storms, and we see them as sunspots, these dark features on the surface of the sun surrounded by bright areas of crackling activity. These are very magnetically active regions of the sun's surface, and this particular wavelength, which is often invisible to our eyes, can still be a delight for some viewers, and it's very, very easy to capture with the right filters. But this image again will have been taken in black and white. The violet colour has been added by the photographer for artistic effect.
Right. Sorry, microphone problems. I decided I get very confused with too many audio and video sources here. Oh, thank you. Hello, Jarvis. Love to talk on planets. Yep. Okay. Jess appears to be the invisible woman, but thank you. Oh, and Ian Whiteley's forehead has joined us. what I've done is... hang on. Oh, I gotta say, I was doing a tutorial with somebody online a few weeks ago, and she was perpetually having audio problems. And she eventually, because no sound was working, she disappeared out of shot, came back, waved an iPad at me, plugged it in, and then said, "Can you hear me now?" So I just said, and just mimed my answer. She looked so furious. I'll point out you laughed before you said it was mean. Oh, hang on. Do we get to mark your answers? It may just be the pleasure of having an answer. It does even in pub quizzes, though. It does even in a real pub quiz. You ask the question and the room goes silent. Yes. I assume the question means has the biggest tilt. See, I feel I should keep quiet at this. But I'm going to tell you, I did mention the crater earlier, and it was not the Gale crater I mentioned. I talked about the Jezero crater. Yeah. Oh, yeah, so good anticipation. And encouraged, the wilder the better. Yeah, she took social distancing a bit too far. There's a wonderful comment to her that social distancing is exactly the same as anti-social distancing. Oh, so many answers.